This lecture is about the isoparametric formulation. What is mesh refining? Mesh refining is the process of increasing the degrees of freedom of the mesh with the purpose to achieve convergence and reduce the numerical error. But what is convergence? A finite element analysis is said convergent when the solution approaches to a certain value when the number of degrees of freedom increases. And what is numerical error? Numerical error is the difference between the numerical solutions and its exact solution. Depending on the mesh quality and the mesh refining process, the numerical solutions may or may not converge to the exact solutions. Hence, the importance to have a good quality mesh at the beginning with the proper boundary conditions, the proper constraints, and then to do a proper refining process. There are two ways to refine your mesh. The first one is the edge refining. That is nothing more than subdividing the elements. Each element is subdivided in smaller elements. The P-refining consists in increase the degrees of freedom of each element. For example, this element has 4 nodes and it can be increased to 8 nodes to get a high order element. Let's introduce the high order elements. So this is the bar with 2 nodes. We know that the interpolation of the displacement in this bar is a linear interpolation. But if you add an extra node to this bar, the interpolation will be quadratic. And the resolution of this element will be higher. The same happens with the 3 element. So here we go from a linear interpolations to a quadratic interpolations. So the base function of these interpolations can be found out from the Pascal triangle in 2D. So in 2D, so you have the T3 correspond to the top base functions in the Pascal triangles, 1, x and y, that is linear interpolations. For the 3, 6 element, we have 6 nodes, so we need 6 base functions. So we need to go to the third row of the Pascal triangle, and then we have a quadratic interpolation. This is for the triangular elements, but we have also the rectangular element Q4 and Q8 that is not showing here, and Q9 that have an element in the middle. So the base function of these elements can be taken also from the Pascal triangle. For example, Q4, we need the linear base functions and we need 1 quadratic functions. So you have to choose the base functions in such a way that it has a symmetry in the Pascal triangle, because you wanted to have the interpolations in the same way in x and y. For the Q9 high order element, so you need to take 9 base functions. You need to take 9 base functions, and you have to keep a symmetry in the Pascal triangle. So this is the base functions. All is the base functions required to the Q9. If you want to have a Q8, so you have to remove these base functions. So this is going to be a kind of cubic interpolations. So to construct these high order elements, it is necessary to go to the isoparametric formulation. That is the modern formulations for finite element modeling. The isoparametric formulations include high order elements with arbitrary shape. These elements include curved shapes. The formulation is used in most finite element software, including strand 7. The term isoparametric, that means same parameters, is derived from the use of the same interpolation functions to define the geometry of the elements and the displacement of the element. In these isoparametric formulations, so the element is a deformation of a master element. So in Q4 isoparametric formulations, we have this as a master element in a intrinsic coordinate system represented by these two Greek letters. And the element itself in the Cartesian coordinates correspond to a transformations from these coordinates to the Cartesian coordinates. The same happened with the Q9 element. This is the master element, and this is the proper Q9 element that can have curved shapes. And we have the T3 element. So we have this standard triangle, and this can be any triangle in the Cartesian coordinates. The 3,6 elements is this one here in the intrinsic coordinate systems, and in the Cartesian coordinate system is going to look like a deformed triangle with parabolic size. 3 parabolic shape size. So in the isoparametric formulations, every point here corresponds to the parameters of this point, and these parameters define a point in the Cartesian coordinate system. Let's illustrate this method with the Q4 isoparametric element. So this is going to be defined as the master element. It's a square in the parametric space, and the squares goes between -1 and 1. So it's a square of size 2, the center corresponds to the center of this coordinate system. So this is called the master element. Then in this element we define 4 shape functions. So these shape functions will depend on the coordinates that are these two Greek letters, eta mu, and this is going to be the 4 shape functions. So every function, for example this one, is 1 in this node and 0 in the other nodes. And the same with n2. 1 here, 0 in the other nodes. Then this is the real element. We call real element because this is the element that you see in strand 7. It's a quadrilateral element. So every point here is a transformation from here to here. So how do we define this transformation? So we use the shape functions. So these shape functions can be used to represent the coordinates of this real element as a function of the parameters. For example, if you take eta equal to 0, mu equal to 0, and you apply these functions, you are going to get the centroid of this real element. So it means that the geometry is defined by these two parameters using these shape functions defined in the intrinsic coordinate system. Now the displacements. The finite element displacement of this element can be expressed as before as a combinations of the nodal displacements here in the Cartesian coordinates, and it happens that the combinations here, the coefficients of these linear combinations correspond to the same shape functions. So it means that the geometry and the displacements are represented by the same parametric formulations. Hence, it's called isoparametric formulation. So the stiffness matrix is what we need to calculate. This is, for example, for plane elasticity. So this is the thickness of the plate. And then we need to calculate this integral over this quadrilateral. So in the isoparametric formulations, we do a change of coordinates from these Cartesian coordinates to this intrinsic coordinate system. So the coordinate transformations will convert this integral into this integral. Here everything depends on eta and mu. The integration is going to happen not in the real element, but in the master element. So this is a transformation of coordinates. And then here, when you do a transformation coordinates, you're going to have an extra term here. That is the determinant of the Jacobian. What is the Jacobian? The Jacobian is this matrix. It's a matrix with the derivative of the transformations. They should be obtained from here. Yes, taking the partial derivatives. And then after you calculate the matrix, you need to calculate the determinant. And in this way, you calculate this integral. So you can see that this integral is a bit more complicated because, okay, the integration area is simple, but these terms make the integration complicated because this is the determinant of this quantity, this plus time this minus this time this. So this is integral over a simple area, but the integrand is complex. So we cannot solve this problem analytically like before. So we need to use a numerical method to find this integral. Now we have to go a little bit back to the numerical integrations. So you probably know some numerical integration, the trapezoid rule, Simpson rule, but probably you didn't hear about this powerful integration scheme that is called the Gauss quadrature. So you know that some integrals cannot be done analytically. It's not like the derivative that you can always calculate the derivative of a functions, but in many cases you have a functions and you cannot integrate this analytically, so you have to do this numerically. So the Gauss quadrature is a method to solve this integral by taking 2 points and perform a very simple formula that is the calculation of these functions in 2 points and apply some magic weights. And these magic weights should make this integral approximately equal to this expression. So the Gaussian quadrature is the integrations, numerical integrations using only 2 points in these functions. This is in 1D. So how do we obtain these points? That is called the Gauss points. And how do I obtain the weights? So the method is very simple. So you apply these equations for these 4 functions, 1, eta, eta squared, and eta cubic. For these cases, you can do the integrations analytically. For example, if I take 1 here, I'm going to have the integral deta between minus 1 and 1 of 1 is going to be 2. And here, f of 1 is 1, because the function is 1. So it's 1, 1, and we have these expressions. That is one equation to obtain the weights, W1 or W2. But we need more equations to solve these weights. So we got to these functions. So we are going to replace f of eta by eta. And then we do the integral of eta between minus 1 to 1 is going to be 0 due to the symmetry of eta. It's an odd function. So it's going to be 0, and here it's going to be f of eta is eta. So it's going to be eta 1, eta 2. And the weights are here. So now I have 2 equations, but I have 4 unknowns. The Gauss points and the weights. So I need another two equations. So we go to eta squared, put this here. So eta squared, integral of eta squared is going to be eta cubic over 3. Calculating the limits is going to give you this one, this 2 over 3. And then here I just replace f of eta by eta squared and you get this one. And then to get the 4 equations, so I use eta cubic. So this integral is 0 because eta cubic is odd. And then I get this expression. So I have 4 equations. And with these 4 equations, I can get the Gauss points and the weights. So I just solve these 4 equations. And then I get the weights in this case is 1. And the Gauss point is 1 minus 1 over square root of 3 and 1 over square root of 3. Then if you have any other functions, any complicated functions, you can approximate these functions by these simple expressions. You only need to calculate the functions in the Gauss points and then make this sum with the corresponding weights. So this is for 1D. So how is in 2D? So in 2D, so you have here, this is the master element for quad 4, and we need to find the Gauss points. After we find we can use 3 Gauss point or 4 Gauss point. Is usual to use 4 Gauss points. So you assume that you approximate the integral with 4 Gauss points, then you have a sum over the 4 Gauss points. So Gauss points should be somewhere here and the corresponding weights. The Gauss points are already given in the lecture notes. So I'm presenting them here. So we can use one Gauss point, and then we need to calculate the functions in the middle. That is 0, 0. So the function is calculated in the middle. And then we have to multiply by the area of the element. That is 4. And this gives us a rough approximation of the integral. A better approximation is using 4 points. So we use 4 points. The Gauss points obtained are these ones. So these are shown in this plot. And the weights are going to be 1. So this is a very good selections. This is a 9-point scheme that is more accurate, but probably we don't need to go too far. So here are 9 Gauss points that are not shown here and the corresponding weights. So strand 7 used 4 Gauss points. So the stiffness matrix, this is the integral that we wanted to calculate over this master element. So the numerical integrations using 4 Gauss points convert this integral in this sum. So we need to calculate the B matrix in each Gauss point and then make the sum of these quantities with the corresponding weights given here. So these expressions give you a numerical approximations of the stiffness matrix that can be used to calculate the nodal displacements just by inverting the stiffness matrix. After you get the nodal displacements, you can calculate the stress. So the stress in each Gauss point can be calculated using this formula. This is the nodal displacements and this is the B matrix calculated in the Gauss point. So in summary, the isoparametric formulation is very powerful. It has very versatile elements, but it involves some numerical approximations. So first, you need to calculate the stiffness matrix numerically using Gauss quadrature, and then the stress is calculated at the Gauss points, and the stress at any other points is calculated by interpolation from the Gauss points.